Hi, I'm Daniel Chan from UNSW Sydney. This is video 3 in a short course on point set topology. And in this video, I want to show you some ways of constructing new topological spaces from old topological spaces. And those two constructions are called the subspace topology and the quotient topology. Okay, so let's do the subspace topology first, and we'll set it up in a slightly more general situation, okay? What we'll do is we'll start with some function f from a set x to a set y, but we're going to assume on the codomain side, this y, it has some topological structure, okay? That's a topological space, but x is just a set. And what we want to do is we want to somehow induce from the topology on y some topological structure on x, a topology on x. And the way we'll do it is through this proposition definition here. Okay, so remember the topology on y is just a collection of subsets, the ones which we call open in that topology, okay? So we want a collection of subsets on x. And what is that collection of subsets on x? Which subset of x do we want? Well, it's given here, this collection here. Okay, so what we do is we let big V rather, range over all the open subsets of y. So we look at an open subset of y, and we look at the inverse image inside x, okay? The inverse image of each open set will give you an open set in this induced topology. And when you look at all of them, I claim firstly that that is a topology, and it's called the topology on x induced by f. And furthermore, it has another property, okay? So now that this has a topology here, these two are topological spaces, and you can ask if this map is continuous. And the point is that with this topology, this induced topology, this map is now continuous. Okay, so let's go through the proof of this. It's quite easy actually, and it uses the axioms of a topological space and the axiom for continuity quite nicely. So we'll assume first it's a topology because it's actually easier to show that f is continuous, okay? And it also motivates the definition of this induced topology. Okay, so suppose that this is indeed a topology. So what we want to show is that f, the inverse image of that, pulls opens back to open. So let's start with an open V inside here, like this one here. And let's look at its inverse image, f inverse V. Well, by definition, this is actually an open set in this induced topology, okay? So in many ways, we defined this induced topology to make sure this f is continuous, okay? And we throw in just as many open sets here as we need, no more, okay? Okay, so the question now just becomes, how do you check that it's a topology on x, okay? So the topology, remember, it has to be closed under finite intersections and arbitrary unions, okay? And the proof of those two axioms is going to be very similar, so I'll just do one of them. The fact that the finite intersection of open sets in this induced topology is indeed still open, okay? So let's take a finite collection of open sets in this topology. So basically we take a finite collection of sets like this. So we have f inverse of v1 up to f inverse for vn, where v1 up to vn are opens inside this y, okay? And we want to show that this is open as well inside this induced topology, so it's f inverse of some open. And the key point here is that the inverse image preserves intersection. So the intersection of these inverse images is just f inverse of the intersection of v1 intersect v2 down to vn. Now these v's, they live in this topological space y, so we can use the axioms of a topological space there to conclude that this intersection of open sets is still open. So this is indeed just an inverse image of an open set in y, so this is open inside the induced topology x, okay? So we do have checked that a finite intersection of open sets in this induced topology is an open set in this induced topology. And I hope you can see very quickly, just by replacing the intersections with unions, possibly with infinitely many, even uncountably many, you have the same verification for the other axiom, okay? So that shows you that indeed you have a topology, and it's also a topology which makes this function or a continuous function. Okay, so what's a subspace topology? Well, that occurs when you look at a very special situation. So one situation that often occurs is where x is a subset of a topological space y. Okay, so this is a in particular set, so you can talk about a subset of that, and you can talk about the inclusion map. Okay, so if you apply this induced topology to this special case of the inclusion map, we get the subspace topology on the domain or this subset x. Okay. Okay, that's the subspace topology. Okay, so let's just have a little look at what that means, okay, in this particular case here. So what are the open sets of this subset, if you talk about this subspace topology? Well, what you need to do is you need to look at F inverse of an open set here. So if you have an open here and you pull it back here, what do you get? Well, it's just the intersection of X with that open set. So the open sets are in X, okay, with the subspace topology are just the intersections of X with the open sets in Y, okay? And one place that we will look at this is, of course, one topological space we have is Rn, okay? So we talk about Rn as is, but of course it has a natural topology, okay? And that's the Euclidean topology, okay? So the open sets there are the Euclidean opens, in other words, the unions of epsilon balls. So in that case, if you have any subset of Rn, okay, what you can do is you can use the Euclidean topology here and the subspace topology on that subset to get you a new topology on that subset, and we call that the Euclidean topology on that subset as well. Okay, so any subset of Rn also has a Euclidean topology, and that's the default topology. So if there's no other topology floating around that hasn't been mentioned, we're using the Euclidean topology in that case. Okay, so that's the definition of the subspace topology, and it shows that a topological space induces a topology on each of its subsets. Okay, so one other proposition that I guess I could have given you before, which is very important and hopefully you could have guessed it, is if you have two composable functions which are continuous, then the composite is continuous as well. Okay, so this is a very familiar fact in calculus, at least for real variable functions on R. And you should expect this to be true, of course, for our definition of continuity for topological spaces as well, okay? So this is something that you always like in mathematics, okay? A continuous map is a kind of structure-preserving map. That's what we'd like to study in mathematics, structure-preserving maps. So if you compose structure-preserving maps, you should get a structure-preserving map. And the proof of this is fairly easy. I'll just indicate it briefly, okay? So you have a composite of functions. So you have a first function and then you apply a second function, okay? What does continuity mean? It means you pull back opens to opens. So if you want to pull back across the composite, what do? You pull back by the second one first, so it sends opens to opens, and then by the first one, it sends those opens to opens. So when you compose that, you send opens to opens still, so the composite is still continuous. Okay, so one of the things that you might want to have a look at, one example of a composite function is suppose you have a function from this y to something else, a continuous function, okay? So if you put the subspace topology on x, okay, then what you can do is you can restrict that function to x, and that's of course just a composite of the inclusion with this function there, okay? And since this is continuous and that's continuous and composite is continuous, that means if you restrict a function to a subset, that will also be continuous, of course, if you use the subspace topology on that subset. Okay, so that's a nice fact. When you restrict a continuous function, you get a continuous function. Of course, you have to know what the topology on that subset is, and for that to be true, you need a subspace topology. Okay, at least this is the natural one to guarantee that that's true. Okay, so that's the first of our constructions for new topological spaces from old one. We want to look at now the dual notion, okay, which is called the quotient topology. And again, the setup is the same. We're going to have a function f from x to y, but there are two differences. The first one is this function has to be surjective. The second one is that now we're going to assume that we have topology on the x as opposed to the y. Here we have the topology on y, and we pull it back to some sort of topology. That's how we induce it to a topology on x. Now we have a topology on x, and we want to somehow push it down to y. Okay, so that's the change. And we can only really do this effectively when this map is surjective. Okay, so when it's surjective, of course, to a certain extent, x contains all the information of y. Okay, so that's part of the reason why you need that. Okay, so this proposition definition tells you what's going on in this case here. Okay, so what is that induced topology? Okay, in this case, we call it the quotient topology, and the quotient topology on y. Okay, so we've got a topology on the domain x. Okay, so now we're going to define it as follows. We're just going to say which subsets of y are the ones which are open in that quotient topology. Okay, which ones? They're the ones which satisfy this condition here. You take this subset of y, v, you pull it back, you look at the inverse image, and you want this to be open. Okay, so you want that to be f inverse of v to be open. So those for which it is open, that's going to be your open in this quotient topology. Those which aren't open, this inverse image isn't open, they're not going to be open in this quotient topology. Okay, so what can we say about this? So firstly, as the name suggests here, of course, this is a topology on y, okay? So now you have a topology on x and y, and of course, one thing you'd like is that the map from x to y is continuous, okay? So we're going to put in a stronger result, in fact, okay? The stronger result is the following, okay? So suppose you want to look at maps coming out of y, okay? So suppose Z is a topological space, and you have a map which is continuous out of y to z. So this is the one which is a new topology on it, okay? So you have a map from x to y, and the point is that if this is continuous, then the composite is of course continuous. And conversely, if the composite is continuous here, then this is continuous. Okay, so that's what's saying. If you want to check that this is continuous, a necessary and sufficient condition for it to be continuous is that this composite from the original x, where you knew the topology, x to y to z, that is continuous. Okay, and I claim that this actually tells you in particular that the function f is continuous. Okay, so why is that? So let's suppose G is the identity map. Okay, G of course is continuous. The identity map, okay, it sends opens to opens, okay, because it just doesn't change the sets at all. Okay, so it sends opens to opens. That's continuous. So of course the composite, the identity with f, so that's just f, is also continuous. Okay, so that's part of what goes on here. Okay, so I won't check the fact that this is indeed a topology, okay? You can check it. It's fairly similar to how we checked it here. What I want to do is I want to show you one of the implications of this if and only if. And that's the one that we're going to use later in this video. Okay, I'm going to show you that if this composite is continuous, then actually this G here, this second factor, is continuous. Okay, so let's do that. So I want to show that this G pulls back opens to opens, assuming that the composite pulls back opens to opens. Okay, so we'll start with an open V inside Z. Okay, and we know that GF is continuous, so let's pull back by GF inverse of V. That's going to be open by continuity of the composite that we're assuming here. Okay, so, but what is GF inverse V? Okay, so we're pulling the open all the way across, so you can pull it back in two steps. You can look at G inverse of V, and then pull that back by F inverse of V. F inverse of G inverse of V, that's open. Okay, so this G inverse of V is a subset of Y. Okay, it's a subset of Y, and when you pull it back by F inverse, okay, that's open. So that tells you that this G inverse of V is open in this quotient topology. G inverse of V is open. That's just the definition of the quotient topology here. Okay, so actually now we can see that this G is continuous because we looked at an arbitrary open inside the codomain V inside Z, and we looked at its inverse image, and that is actually open. So since it preserves these opens, then G is continuous, and that proves this part here. Okay, so let's have a little look at an example of a quotient topology. It's less natural than just looking at subsets. This is probably the first example that you should see in this case, and that's basically the torus. Okay, so our starting point, we're going to start with the X is a topological space. Okay, and that's going to be a square. And the square that we'll pick here is going to be the closed interval 0 to 2 pi, cross 0 to 2 pi. Okay, so that's a square. It's a subset of R2, so it has a subspace topology. Okay, that's easy enough. Okay, so the opens here are just basically intersections of open sets in R2 with this X. Okay, so that's what we have. And now we need a surjective map coming out. And how will we do that surjective map coming out? We'll do it as follows. Basically, you're going to look here. We're going to put an equivalence relation on this X. And that basically identifies points of X. We'll see this in a moment if you haven't seen this idea before. Okay, so what this X mod, this equivalence relation is, it's the set of equivalence classes. Okay, and what is the map here? Basically X gets sent to the equivalence class of X. So the set of all things which are equivalent to x. Okay, so remember, an equivalence relation partitions this x into equivalence classes. Okay, and sending x to its equivalence class, of course, that's surjective. This is just a set of all these equivalence classes, so it's a set of all these brackets of these x's, and so of course it's going to be surjective. So we have a surjective map here. Okay. So let's see what we want to do with this surjective map. What is this relation? So basically what we're going to do, so the arrows here are not part of the actual space, it's just to suggest the equivalence relation. So you've got two arrows pointing this way, and that means that we're going to identify the bottom edge with the top edge. And that's represented by this relation here. So the relation is going to be generated by the relations here. Okay, it's the equivalence relation generated by this. So you have to throw in the reflexivity and the symmetry, okay, and the transitivity. Okay, so let's look at x0. So that's on the y equals 0. So that's a point like this. Okay, we want to identify that. That's going to be related to x2 pi. So the same x here, but it's up 2 pi. So these 2 points will be identified. And more generally, another point here will be identified by the corresponding point on the upper edge. Okay. Similarly, we want to identify the left-hand edge with the right-hand edge. So 0y is going to be related to 2 pi y. So the 0y, so it might be a point like this here, is going to be related to 2 pi now y. Okay. So the best way to think about these equivalence classes, the set of equivalence classes, is if you just identified these 2 points, these 2 points, these 2 points, and so forth. And similarly, we've identified these 2 points and the corresponding points on either side. So I've drawn this as a torus, okay, and that's hence the name there. And you'll see why in a moment, okay, if you haven't seen this before. So I've got a rectangle here as opposed to a square, but you can see a similar thing sort of happens. So now you want to identify corresponding points at the top and bottom. So basically you want to glue this edge to this edge. And when you glue that edge to that edge, what do you get? You'll see very simply that, of course, you just get a cylinder like that. Okay? You glue the top edge to the bottom edge, you get some cylinder, okay? So the top edge to the bottom edge, you get some cylinder, okay? And of course, there's another identification that you need to make. The left-hand edge and the right-hand edge gets identified as well. So if you bring this one around, so I need to have actually a bendy balloon rather than paper to do this, and you identify those two ends, I hope you can see you get a torus, okay? So that's the outside of a donut, okay? So of course, the way I've drawn it as a set, you can think of it as a torus, but what I want to say is that, well, firstly, you can think of a torus inside R3, and that is a natural object. It's got a subspace topology because it's a subset of R3, and I want to say that essentially this quotient topology on this quotient set is basically the same. But to do that, I need to give you another definition. Okay, so the definition that we need is the following. Let's suppose you have a continuous map F from a topological space X to a topological space Y. I want to say when it's bicontinuous or a homeomorphism. Okay, it's going to be bicontinuous or a homeomorphism if the following conditions hold. So firstly, it's going to be bijective. Okay, so that means that it has an inverse function essentially. And the second condition is that this inverse function has to be continuous as well. Okay, so this notion is essentially the notion of an isomorphism in the category of topological spaces. Okay, so topology is basically the study of geometric objects, but one where you treat homeomorphic objects as essentially the same. Okay, so let me unravel the meaning of what's going on here. So remember, continuity means that if F is continuous, its inverse image sends opens to opens. We also want F inverse to be continuous. So its inverse image now is just F. So the actual function here now sends opens and the image will be open. So in other words, F continuous sends opens here back to opens, and F inverse continuous means that it sends opens to opens. Sometimes the functions which send opens to opens, they're called open maps. Okay, so in this case, what we find is that this F, okay, it's a bijection, so it's an isomorphism of sets, okay. That isomorphism, that bijection gives you a dictionary between those two things. But also in the case of a homeomorphism, you have a dictionary between the whole topological structure as well, because F and inverse induce inverse bijections on the collections of open sets on the two sides. So one set opens here, and the other one set opens back to opens here. So there's a complete bijection on the collections of open sets, okay? So really, they have the same structure, but there's a change of name from the objects here to the objects here via this F. Okay, so with this definition, we can make sense of the fact that that quotient space that we looked at here, basically this square where we identify the top edge, bottom edge together, and the left-hand edge with the right-hand edge, okay? So that's a space. It's a set now, it's a quotient set, and since it has a quotient topology, it's a quotient space. Okay, so we can look at that, X mod this tilde, and I want to say that this is actually homeomorphic to the torus inside R3. Okay, so let's be specific by what we mean by our torus. I'll denote it with this double barrel T. So I'll start in the YZ plane, and I'll pick a circle like this, okay, whose center is along the Y-axis, say distance big R out, and then you have the circle here, which is little r. Okay, so you have that circle, and what we're going to do is we're just going to take that circle and we're going to spin it around the Z-axis. Okay, so that gives you now a torus inside R3. Okay. So of course, being inside R3, it has a subspace topology. Okay, so that is a topological space. And I want to show you how these are homeomorphic. I can't give you complete proof, but I can give you something which more or less tells you what's going on. Okay, so the way we'll do it is the following. We have to construct a homeomorphism from this quotient space to this torus. So to start off with a continuous function. So how do I do that? The way I'll do that is actually, remember there's a quotient map from this square 0 to 2 pi cross 0 to 2 pi down to here, and I'll construct this top map first, okay, and show you how it induces a map from the quotient to here. Okay, so what's this top map here? What will I do? So firstly, what I'm do, the elements inside here is essentially two angles. Of course, the angles 0 and 2 pi have been written out differently. Down here, they're the same, they're really just angles, okay, so this is just a set of angles, pairs of angles, right? But here the angles 0 and 2 pi are written differently, and here the angles 0 and 2 pi are written out differently. So you've got a theta and a phi here, okay? So let's look at the various bits. I'm going to break this up into two bits, one according to theta, one according to phi. So the first thing is, what does it mean to rotate about the z-axis, okay? So we can represent that using a rotation matrix, okay, as follows. So this is a rotation matrix, okay, it's a rotation matrix through an angle of phi. And what it does is it keeps, since this one here is in the third coordinate, it's the third row, the third column, it's keeping the third coordinate, the z-axis fixed, okay? And it rotates in the xy plane, okay? And the angle of rotation is phi. Okay, let's look at the theta bit. That's given by this vector here. This vector is in the x equals 0 plane inside xyz space, okay? So let's see where it lands inside here. It lands inside, well, the y value is big R plus little r cos theta. So big R plus, if this is theta, r cos theta will be the y value along here. So it's you drop a perpendicular, okay? And r sine theta is just the height. So basically, of course, I hope you can see easily enough, this is elementary calculus, that as theta goes from 0 to 2 pi, basically you sweep around the circle from here over to here, okay? So if you look at these maps, let's look at them separately. Firstly, theta to this thing here, it's almost a bijection. It's 1-to-1 everywhere, except for the 0 and the 2 pi get mapped to the same point. So it's 2-to-1 there, but it's 1-to-1 everywhere else, okay? It's a bijection everywhere else. Similarly here, the map from phi to here, so 0 to 2 pi, that's what phi ranges from, to this rotation matrix. Everywhere, it's going to be a bijection, except for the 0 and the 2 pi, they're the same angle, so they get mapped to the same point, okay? And I hope you can see as a result, basically what happens is that, so firstly, we have a continuous map from here to here, because this is just matrix multiplication of two continuous functions, okay? These are trigonometric functions, they're all continuous, all the entries here are continuous, okay? So it's a continuous function of theta and phi, all the entries, and when you do the matrix multiplication, what you get is a continuous function, okay? So that's a continuous function from this Euclidean topology to this Euclidean topology over here. Okay, so having said that, I hope you can also see that this is almost a bijection as well, by what I said. And the only times it's not a bijection, of course, is when 0 equals, is the 0 here in the 2 pi, they get identified to the same point, and similarly over here. So what I claim is that that means that you have a bijection from this quotient set to this one here. So this set of equivalence classes to here, okay? And it's through this map here, okay? So how does that work? So you send the equivalence class containing P, so most of the time there will only be one element inside there, so that's all the elements here. But sometimes it will have two, like these two, or sometimes it will be four, like these, the four corners of this square. That'll be 4, okay? So what you can do is you can send this to what? You can send this to F tilde, so that's an F tilde rather, so that's my map, F tilde of this P. And of course, when you do that, you have to check that this is well defined, because you could have picked a different representative of this equivalence class. But the only way you can change the equivalence class is basically if one of these was either 0 or 2 pi and you swap to the other one. And of course, since those two have the same value, right, when you change from 0 to theta, from 0 to 2 pi or the other way around, or similarly with phi, you get the same value. This is well defined. And of course, now what you find is that all the things which were 2 to 1 or 4 to 1 now become 1 to 1 when you pass to this quotient. So now we have a bijection here, okay? So the next thing to check is that this is actually a continuous map, which is also a homeomorphism, so its inverse is also continuous. So unfortunately, I won't show you how the inverse is continuous. There are cheap ways of doing that if you know a little bit more topology, and that I will show you later. But to show this is continuous is quite simple, actually. And it just uses the proposition definition 2, where I define the quotient topology. Okay, so remember, if you want to check that a map coming out of a quotient space is continuous, all you need to do is to check that the composite with the quotient map is continuous. So this map is continuous here. And the point is, like I've said, this is continuous. So hence this is continuous as well. Okay, so unfortunately you do actually need to check that the inverse is continuous, and you can either do that directly, it takes a little bit of work, I won't do it, or you can try to apply some more powerful theorems to show the inverse is continuous. Okay, but that's very nice now that you have this quotient example of a quotient space, so a quotient set, a set of equivalence classes with a quotient topology, and we can identify it with this torus, which has this subspace topology. Okay, and in this example you might have thought, well, this is a rather complicated way to describe the torus. It seems a lot easier to understand the topology of the torus by thinking of it as some subset of R3, okay? But actually this is a general procedure which allows you to construct really interesting topological spaces. And the next one I want to show you is something very similar to this. I'm just going to tweak it ever so slightly to give me something called the Klein bottle. And we'll define it the same way. We're going to start with this x, which is this square here. Okay, that's 0 to 2 pi cross 0 to 2 pi. And again, I'm going to identify the left-hand edge with the right-hand edge. So that's why I have the double arrows going up just as before. And we'll do that the same way. Okay, we'll put an equivalence relation. And in the equivalence relation, we'll have 0y as before. So that's 0y. Is going to be equivalent to 2 pi y. Okay. What's different now is that the way we identify the top edge and the bottom edge is going to be different. So now the arrows are in opposite directions. So what does that mean? Okay. So before we had x0 here was going to be equivalent to the corresponding point up here. But now, since the arrows are in the opposite direction, we want to say we're going to go a similar amount along the arrow. So you've gone this way along the arrow, you're going to go that way along the arrow. We're going to identify it with that point over there. So this gets identified with that, this one with this one with this, and so forth, like that. Okay. So that's the only difference. Okay. Well, of course, if you try to do this, it's quite tricky. Okay. So before you glue the top edge to the bottom edge like this. Now what you need to do is you need to reverse it so that you have to twist it around. And you'll find, of course, when you do that first one there, you'll get something called the Mobius band. Okay. So in that case there, you'd think, well, it's pretty hard for me to imagine what you get. And part of the reason why is it doesn't naturally embed inside R3. And that's one of the reasons and one of the things that's so great about this quotient construction here, okay? You can actually put a geometry nicely on that quotient set, okay? Even though you can't imagine it as a subspace of something else. So in the next video in this playlist, I want to show you how to create even more topological spaces from other ones.